Chapter 15.5 is all about calculating the equilibrium constant. And this has to do with knowing the equilibrium concentrations. So to do this, you're going to look at the problem and find any initial and equilibrium concentrations. Now they're going to give you probably many or most of these. So once you know these, you're going to find out what the change in concentration is. So you're going to calculate the change in concentration. Then under the balanced chemical reaction, you're going to find the change for all the other reactants and products. So basically you're going to know all initial concentrations, and you're going to know at least one equilibrium concentration. And then from that, finding the change, and then finding the rest of the equilibrium concentrations of your reactants and products. Then using your initial concentrations and the changes, find the equilibrium concentrations of all the species. Then you can plug that into the Kc expression to find the value for the equilibrium constant. So let's practice. I have a closed system that has 1 times 10 to the negative third molar of hydrogen. 2 times 10 to the negative 3 molar iodine, and is allowed to reach equilibrium. So we can see we have hydrogen plus iodine goes to 2 hydrogen iodide. So because it doesn't tell us how much hydrogen iodide, we can basically assume that's going to be 0. Which makes sense. If I start with some reactants, I probably don't have products. After the mixture is allowed to reach equilibrium, the equilibrium concentration of hydrogen iodide is 1.87 times 10 to the negative 3 molar. So that's an equilibrium concentration. And then calculate Kc at 448 for the rest, for the whole reaction anyway. So real quick, let's just write our Kc. Kc equals our products, which are hydrogen iodide, to their coefficients, so squared, divided by our reactants. So H hydrogen times iodine to the first. Okay, so we're gonna have our ICE table, which is initial, change, and equilibrium. So for this, you're going to know all of the initials and at least one equilibrium. And from knowing an initial and an equilibrium, we can find the change. So we know that we went from 0 to 1.87 times 10 to the negative third molar for hydrogen iodide. So we gained 1.87 times 10 to the negative third. Great, and that's a product, so it went up. And now I'm going to draw a little line here showing the difference between reactants and products. So if I gained that, and I'm actually going to put, I have 1-to-1 for those and 2 hydrogen iodides here, okay? So if I gained 1.87 times 10 to the negative third, that means that I lost half of that in iodine and hydrogen. So that means I lost, so half of 1.87 times 10 to the negative third is 9.35, so I'm going to lose, minus 9.35 times 10 to the negative 4. Both of those, because their numbers are 1-to-1, I'm going to lose that. I could also say that for every 2 of those, I have 1, so I can multiply by a half. If you need to do that, that's fine. Okay, so then after doing that, I will go through and do the change. So I start with 1 times 10 to the negative third. I subtract 9.35 times 10 to the negative fourth, which means left over I have 6.5 times 10 to the negative 5 molar of hydrogen. It means I have 1.065 times 10 to the negative third molar of iodine, and I know how much hydrogen I have. So now I can plug those values in. So these are the values we need to put into our K expression. So I'm going to put 1.87 times 10 to the negative 3 squared divided by 6.5 times 10 to the negative 5 and 1.065 times 10 to the negative third. And when I put that into my calculator, I get a value of 51. So that means that I favored products, which makes sense because I have more products than I have reactants. I could do the same thing with Kp. So here I have gaseous bromochloride decomposing to bromine and chlorine gases in a silk container. Initially, I have at 500 Kelvin, I have a partial pressure of bromochloride of 0.5 atmospheres. So I'm going to plug that in here. At equilibrium, the partial pressure of bromochloride is 0.04 atmospheres. Calculate value of Kp. So notice it didn't tell me how much chlorine or bromine I have, so guess what? I probably have 0. Perfect. Okay, so notice that Kp is, for this reaction, is going to be the pressure of bromine product times the pressure of chlorine product divided by the pressure of bromochloride squared reactant. Okay, so I need to find those equilibrium values. So I know bromochloride, and so I know my initials. So I want to find out how much of my bromochloride did I lose. So I went from 0.5 to 0.04. So that means I lost, so minus 0.46 atmospheres. Okay, so for every 2 of those, I have 1 of the other things. So that means I'm going to gain half of as much. So I'm going to gain 0.23 on both sides because they're 1-to-1. And that's where I gain. So now I have 0.23 of my products. So now I can plug those in for my pressure. So I have Kp equals the pressure of bromine, which is 0.23 atmospheres, times 0.23 for chlorine, divided by 0.04. And we can see we have much more products than we do reactants at this equilibrium. So that means my value should be greater than 1, and indeed it is slightly greater than 1. I have a equilibrium constant or pressure constant of 1.32. Just for the hell of it, let's also find Kc. So remember, Kp equals Kc times RT to the delta N. Notice I have 2 products of 2 molecules of gas as products, 2 as reactants. So delta N equals 0. So notice Kp equals Kc to the 0. So RT to the 0 is 1. So notice Kp equals Kc. So they'll be the same. Okay, that's basically it for this. So put in the initial things you have, find the change based off an equilibrium value, and then plug in the rest of the equilibrium values into your expression.